Hello, everybody. Welcome back to another topic with calculus. Today, we're going to be talking about the derivative and the instantaneous rate of change, or just rate of change for the time being. So, the idea here is that we've been playing around with limits for the last 2 or 3 sections, and now we're going to apply it to what we did back in algebra, and see if we can come up with something new then. So here's what I want to do then. Let's go ahead and say that I have a graph, okay? And here's your graph. We'll go ahead and call f of x. What I would want is to find what is the equation of the tangent line, or maybe just what's the slope of the tangent at a certain point where we go ahead and say x is equal to a then. So the tangent line, meaning that if you close in very, very close within a small little window near x is equal to a, you can see that the tangent line and the actual curve are almost like one and the same. Tangent back from geometry means that it only touches that curve f of x at that point x equals to a locally at only one single spot, which is there. So here is how we can approach it then. Now, in order to get the equation of a line, going back to algebra once again, we need to have 2 points to use in order to figure out what the slope is. Slope, if you remember, is supposed to be the change in y divided by the change in x. So the way we solve for it is y2 minus y1 divided by x2 minus x1. But the problem here is that we don't actually have 2 points to work with. We only have 1 point because, again, we're looking for the slope of the tangent line, meaning that it only touches the curve at 1 point. So what we can do is the following. Let's go ahead and pick an arbitrary point a little bit further away, maybe to the left or maybe to the right. So in this case, let me just go ahead and say to the right of it. In terms of like how far away, we'll go ahead and denote that as h for the time being. So then that means that the x value over there, h units away from a, is going to be a plus h. In addition, we can also look at its y value. The y value at a, if you're plugging into the function, well, that is going to be f of a. So that is going to be this guy over here. Now, plugging in a plus h into the function, then that means that this y value would then be f of a plus h. So now we can go ahead and create another line right here. And that line right here, the red one that I just created, that is what is known as a secant line. Okay, so that is known as a secant line, meaning that it touches the curve twice locally around that value of x is equal to a. The secant line, if you notice, it's very, very close to the tangent line that I actually want. So we're going to go ahead and use that in order to figure out what we actually need then. So here, let me just kind of write that right now. The blue is going to be the tangent line that I'm trying to solve for. And the secant line is basically what I'm going to use in order to figure out what the tangent line is. So let's go ahead and solve for the slope then of the secant line. Okay, so the secant is going to be f of a plus h minus f of a, all divided by h in this case, because again it's going to be the change in y divided by the change in x. Now you can see the change in y is going to be the difference between these two values, so that's where this part comes from, and the change in x, that's going to be the h that's over here, so that's where that comes from. So again, this gives you the slope of the secant. And what I would like to do is I would like to move that secant line a little bit closer in towards the left, or better yet, move that red point a little bit closer in towards the left so that it's closer and closer to the blue point of the point of tangency. Now in this case, this is where the limit that we've been doing so far comes in. So what I'm trying to say is that in order to get the tangent that I want, okay, I would take the formula of the secant that we just came up with, which is f of a plus h, okay, minus f of a, all divided by 8, and I'm going to go ahead and now apply the limit that we've been learning so far. where it says limit as h approaches towards 0. And as you can see, h cannot equal to 0 because then the 2 points would be the same. But ideally, we would like to have h go as close as possible to 0, so then that way we can estimate what is this tangent slope is going to be then. Okay. So that is going to be what we're going to be using, and that is one of our formal definition of the derivative, which we will talk more about within the coming section. So let me go ahead and write out the following then. So the limit as limit as h approaches towards 0 of f of a plus h minus f of a, all divided by h. So that is going to be the tangent, okay, slope at x equals to a. Okay. Now, another way of looking at it also is the following. We can then, let's, instead of saying the point that we're going to look further away is called f of a plus h, instead, we're just going to go ahead and say f of x then. So here, let me go ahead and draw underneath over here the same graph, okay? So something that looks like the following. Okay, so here is again, we're going to say that that is the point of tangency that I would like. And I am going to just pick any arbitrary point that's over here. We'll go ahead and call x right now, okay? So then that means, once again, okay, the y value over here is going to be f of a. And then over here is just going to be some arbitrary point on the curve of f of x. So that's just going to be plano f of x. Similarly then, if I want to find out what is the slope is going to be equal to f of x minus f of a, all divided by x minus a. And in this scenario, this would then give us the same answer that I have right above it if I allow x approach towards a as a limit then. So if I say the following, limit as x approaches towards a of f of x minus f of a, all divided by x minus a, this would also give us the tangent slope also. Okay, so tangent slope at x equals to a. So what I just did was I basically gave you two ways to solve for the slope of the tangent at a single point. So now let's go ahead and see if we can apply all of this then to what we're doing then for this section. Okay. So let's say for this problem right here, I want to find the slope of the tangent line for y is equal to x squared plus 7 at x equals to 5. So I'm going to go ahead and show you both methods, and then you guys can choose which method you want the best, whichever one works best for you guys then. Okay. So let's go ahead and start with method number 1. Which is basically going to be using the tangent is equal to the limit as h approaches towards 0 of f of 5 plus h, and then minus f of 5, all divided by h. Okay, because in this case, keep in mind that my a value, where I want to find the slope of the tangent line, is equal to 5, right? And we're calling f of x the function x squared plus 7. Okay, so using this method right here, let's go ahead and plug everything in. So limit as h approaches towards 0, f of 5 plus h. So that means that in here, in this function, I am going to go ahead and plug in 5 plus h then. So f of 5 plus h is going to be equal to 5 plus h quantity squared plus 7. So that's going to be my first part right here. So 5 plus h quantity squared plus 7. Now I'm going to take that and then I'm going to subtract f of 5. And f of 5, that basically means that I'm going to take f and plug in 5 for x and solve for what I have there. So that would give me then 5 squared plus 7, which is equal to 25 plus 7. So that's going to be equal to 34. So minus 34 over here, all divided by h. So now, if we clean that up a little bit, let's see if we can get something nice and clean. Limit as h approaches towards 0. For this part of 5 plus h quantity squared, I have to expand it out using FOIL. So that's 25 plus 10h plus h squared. And if I take 7 minus 34, that would give me minus 25 all over h. So note, in this case, we have the 25 and the 25 cancels out. And what's left in the numerator are a bunch of terms that contains h, which tells me I can now divide through by that h that was problematic. See, this is actually very similar, if not exactly identical, to the limit problems that we were doing in the past couple of sections. So now if I divide through by h by both for both those terms, I am going to be left with 10 plus h. And at this point, once I divide it by h from both terms, I can now allow h to be equal to 0. And in that case, we are going to get 10 plus 0. So the answer is equal to 10. So that right there is going to be our slope at x equals to 5 for the function y is equal to x squared plus 7. Okay. Now, let's go ahead and use the second method to see if this one works better for you. So method number 2, right, is instead of using this equation right here in order to find the slope at the instantaneous point, we're going to use this one right here. So let's go ahead and label them for right now. We'll go ahead and say this is going to be kind of like equation number 1, and let's say that this guy is going to be equation number 2. So what I want to do now is I want to use equation number 2 over here. Okay, so limit as x approaches towards 5 of f of x minus f of 5, all divided by x minus 5. So again, if I solve for this limit problem, then I should be able to solve for the slope, which would hopefully then be the same answer as what I just got right above it. Again, replacing f of x with a function. So limit as x approaches towards 5. We have x squared plus 7 for f of x. And earlier we solved for f of 5, which turns out to be 34. So I'll go ahead and make a direct substitution as well. So x minus 5 is still in the bottom. Now, in the numerator, we see that the 7 and the negative 34, we can combine that, giving us x squared minus 25 over x minus 5. And as luck would have it, notice the top part is a is a difference of square, which I can factor. So limit as x approaches towards 5, we have x plus 5 on the top, x minus 5 on the top, both factors, divided by x minus 5. The x minus 5 cancels from both top and bottom, which will be the problematic part. So now limit as x approaches towards 5 of x plus 5. We're going to go ahead and use a direct substitution because this is a polynomial. So 5 plus 5, so the answer is equal to 10. So same as what we have above. Okay. So as I said, you can choose whichever method you want. So right now, it's really up to you as to which kind of algebra you want to do. Now, let's try that with a different equation over here. Find the equation of the tangent line for y is equal to 3 over x plus 1 at x equals to 0. So I'll just go ahead and pick a method, and then we'll go ahead and solve for it once again. So let's see. I'll go ahead and say method 1 for the time being. Okay. So for method number 1, we have the limit as h approaches towards 0. Okay. Of f of 0 plus h minus f of 0, all divided by h. Note that a is equal to 0 because that's where the point of tangency is equal to. And also, I am going to write over here, that's right, f of x is equal to the function 3 divided by x plus 1. So making my direct substitution again, limit as h approaches towards 0. F of 0 plus h, so that means that I'm really just solving for what's f of, let me go ahead and write it right here just in case. F of 0 plus h, which actually is the same thing as saying just plain old f of h, that's going to be 3 divided by h plus 1. So that is going to be replaced over here, 3 divided by h plus 1. And then we have minus f of 0, plugging 0 into our function of f. That's going to give us 3 divided by 0 plus 1, which is equal to 3. So minus 3, and all divided by h. Now, in order to clean up this mess over here, what I normally like to do is multiply by the part that is problematic to both top and bottom. So the part that's problematic is the factor h plus 1. Okay, So if I multiply that to both top and bottom, then hopefully we are going to get something that's a little bit cleaner to mess with algebraically. So limit as h approaches towards 0. The top part, the top left part, if I multiply h plus 1 into 3 divided by h plus 1, that's going to give me just plain old 3. Minus 3 multiplied by h plus 1, all divided by h times h plus 1. And if you remember what I said in the last video, I try not to multiply anything out in the denominator, meaning I always want to keep it in factor form because that's always the best when it comes to manipulating algebra. Okay, top part, keep cleaning it up, trimming it as much as you can. So 3 minus 3h minus 3, all divided by h times h plus 1. The 3's can cancel out. Then you have the h, right, the top, and the h that's on the bottom. So those are going to go away too. So what's left now is as limit as h approaches towards 0 of negative 3 divided by h plus 1. And remember, the whole purpose is to let h equals to 0, and we got rid of that problematic part. So now we can go ahead and apply direct substitution. So we're going to get negative 3 divided by 0 plus 1. So the answer is equal to negative 3. Okay, so that right there is going to be the slope. Now, normally, I guess we would be done if we were looking at the first problem that we did. But this one, you have to be a little bit careful because this is find the equation of the tangent line. So what that means is I'm kind of like halfway done. Well, at least I did the harder half anyways. I know the slope. I need to find a point in order to get the point slope form, right? So I need to know what is the coordinate over there. Well, we know what is the x value already because that says at x equals 0. So we just need to know what the y value is. Well, fortunately, we have that over here as well also because that was one of the part of the procedure in order to figure it out from earlier. So the point of tangency is going to be at 0, 3. So now we have everything. We have the slope, we have the point of tangency. So now we can put it all together then. So using the point slope form, y minus 3 is equal to negative 3 times x minus 0. So cleaning that up a little bit more, so then we get y is equal to negative 3x plus 3. So that's going to be the equation of the tangent line then, okay, of the tangent line. And just to kind of show you, actually, let me just be a little bit more clear. Equation of the tangent line at x equal to 0. And just to kind of show you what all this means graphically, here's what things look like. So here is the graph of y is equal to 3 divided by x plus 1. If I were to give you kind of like a rough sketch of it, we know that the vertical asymptote is located at x equals to negative 1. So that is somewhere over here. Okay. The end behavior, or the horizontal asymptote, as some people would call it, is y is equal to 0. So that means that's just the x-axis. And in terms of like, just plugging in a value, right? If I remember, just plug in like say x is equal to 0, you're supposed to get 3. So that's like somewhere over here then. So that point, let's just say, is approximately 0, 3. So if I sketch out the graph, this is basically what it looks like. Okay, so that's going to be this guy over here. And so what I just solved for, the equation of a tangent line at x equals to 0, is the following. And let me go ahead and use red for this one so I can make it a little bit more distinct. So I basically solved for the equation of the tangent line that is located right here. And again, the tangent line is the line that touches the graph exactly at that one single point only, locally, at x equals. Sorry, my graph isn't exactly that best, so I do apologize about that. Okay. All right. So now let's go ahead and look at this last example over here, which is more of a modeling problem or a word problem for the most part. Okay. So here we start with the displacement of a jumper off the top of a building can be modeled by the function h of t is equal to negative 32t squared plus 4t plus 240, where t is the number of seconds after he jumped and h of t is the height in terms of meter. I want you to find what is the average velocity between 1 to 2, okay, between t is equal to 1 to 2. Now, thinking back to, I guess, the physics days, if you're trying to find velocity, right, then that is going to be a rate of change of the displacement over time. So here, let me just kind of write it out here. So the average velocity, what I'm trying to solve for, is supposed to be the change in the displacement, this divided by the change in time. Now, the change in time, well, that is going to be 2 minus 1 because it's from 1 to 2. Now, the displacement, well, that's where the displacement function h of t comes in. That's going to be h of 2 minus h of 1. So we just need to figure out what those are numerically, and we're pretty much all set. So h of 2, we're plugging 2 into the equation. That is going to give us negative 32 multiplied by 4 plus 16 plus 240. And then all that minus h of 1, which is going to be negative 32 plus 4, and then plus 240. And all divided by 2 minus 1, which is the same thing as 1. Let's see, some of these stuff can cancel out. We have the 240s, they can cancel each other out. We have negative 32 and then multiplied by 4, that is equal to 128. So let's go ahead and write that out. So negative 128, and then plus 16, and then plus 32, and then minus 4. So keep trimming as much as we can. Negative 128 minus 16. That is actually, wait, let me just do this one instead. Negative 128, and then add it with these two together. That's 48 minus 4. So let's see, 128 negative minus 48, that's equal to negative 80, and then minus 4 is equal to negative 84. And in terms of what is the unit for this, remember the unit for the h of t, that is in terms of meters, and for t, that is in terms of seconds. So then that means that this is going to be in terms of meters per second. Okay, so that will be then our average velocity. Now, this time in part B, I said I want to find the instantaneous velocity at t is equal to 1. So this is where we apply the tangent thing that we've been doing so far into this, because again, the instantaneous velocity is saying how fast are you going at that instantaneous moment at t is equal to 1. So unlike in part A where we saw for the secant slope, in part B, I want you to find the tangent slope, because again, we only have one single point to work with, whereas in part A, we have 2 points to work with. Okay, so then here we go. Limit as t approaches towards 0, as h approaches towards 0, of h of 1 plus h minus h of 1, all divided by h. Okay, so we can either use this method or we can use the other method. Limit as t approaches towards 1 of h of t minus h of 1, all divided by t minus 1. So we can use method number 1 or we can use method number 2. And since we used method number 1 earlier, why don't we just go ahead and use method number 2 in this case, just to get a different variation. So we'll go ahead and replace the equation with what we see over there. So limit as t approaches towards 1 of negative 32 t squared, and then we have plus 4t, and then we have plus 240, and then minus h of 1. Now h of 1 earlier we did solve for, and I do believe that was equal to negative 28. Okay, so that is equal to negative 28. And then all divided by t minus 1. Okay, keep cleaning it up as much as we can once again. So limit as t approaches towards 1. Negative 32 t squared, and then plus 4t. And then we have, let's see, the negative and negative cancel out. So that's going to be plus 268, all divided by t minus 1. So now we're going to have to divide through into that to see what we get then as an answer. Now, unfortunately, this is something where you're going to have to do a little bit of factoring in order to figure out. So we can go ahead and do that, or you can go ahead and do long division. Since, I'm not exactly good at factoring, we'll just go and do long division just to see what we get. Okay. Let's see. Hopefully this will all work out. Negative 32t squared plus 4t plus 268. And then we have t minus 1. And again, you can avoid all of this if you know how to factor the top part, which is something that I don't know how to for the time being, just because the numbers are a little bit too big. Okay, so let's see here. Let's see. What multiplied by t would get me negative 32t squared? So that's negative 32t. So negative 32t squared, and then plus 32t, and then take the whole thing and subtract it. So let's see, the 32t squares will cancel out. This will give me minus 28t. And now we're going to go ahead and bring down to 268. So that will then give me, let's see, minus 28 over here. And I am going to plug in that. So that's negative 28t, and then plus 28, and then all that's subtracted through. So all that is gone, all that is gone. So it looks like we're going to get 240 then. So then that means we will get the following. Plus 240 divided by t minus 1. So it looks like I am going to be running into a little bit of trouble here. So maybe I shouldn't have taken this route. Okay, well, lesson learned in this case then. Well, tell you what, let me go ahead and put method number 2 aside. When I find a mistake, I'll go back to it. Let me just go ahead and use the first one in this case. So maybe the hubris, my hubris got the best of me. It happens sometimes. Limit as h approaches towards 0. Plugging h of t 1 plus h into the equation. Okay, so that is going to be negative 32 1 plus h squared, and then we have plus 4 times 1 plus h, and then we have plus 240. Okay, and then minus h of 1. So let's see, h of 1, that is supposed to be, oh, I think I see my mistake from earlier actually, because h of 1 is actually something else. H of 1 is going to be this whole thing. So that's where I made the mistake. Okay, so I can probably clean that up in a little bit then. Okay, so let's see here if I can write that out. Negative 32 plus 4, and then plus 240 then. Okay, and then all divided by h. Okay. You know, I always tell my students this is a problem. I can do calculus, but I can't do regular algebra because, you know, the higher up you go, the worse you are at the lower end stuff. And it's just, you know, it's always like it's a very unfortunate phenomenon. Okay, so let's see here. Let's go ahead and clean this up as much as we can. So 32, and then we have now 1 plus 2h plus h squared. And then we have plus 4 plus 4h. And then looking at what we have right here, the 240s would cancel each other out. And then we have plus 32. And then we have minus 4, all divided by h. Okay? Okay. So limit as h approaches towards 0 of negative 32. And then plus, actually it's now going to be a minus. So let's go ahead and erase that part. Okay. So let's see, negative 32, and then minus 64h, and then minus 32h squared, plus 4h, and then we have the 4 and the negative 4 cancels out, and then we have plus 32, all divided by h. Okay, and I know this is working out because I noticed the negative 32 and the positive 32 cancels each other out. So let's see here, limit as h approaches towards 0, 64h negative, and then plus 4. So that's going to give me a negative 60h, and then minus 32 h squared, all divided by h. Bear with me, it looks like we're almost done. The h now can be divided through from both top and bottom. So h approaches towards 0, we have negative 60, and then minus 32h then. And now we can go ahead and let h equal to 0 by using direct substitution. So then that means negative 60 plus 0 is my answer. So that means negative 60, and meters per second, that's going to be my instantaneous velocity. Okay. Now, in terms of what I did wrong in method number 2, I see it right now, and I'm going to go ahead and change it too. Let me go ahead and go back here and change that part because h of 1 is what I did wrong. So let me go ahead and clean all this guy up, okay? And hopefully we'll get something nice and clean then for you guys. Let's see. So h of 1, again, it's supposed to be this thing right here, negative 32 plus 4 and then plus 240, okay? So let's see here. Limit as t approaches towards 1, negative 32t squared plus 4t and then plus 240. And then this is going to be the 240 and the 240 cancels out again. So that gives you negative 28 and then it will be plus 28. And then it's going to be, let's see, all divided by t minus 1. Cleaned up as much as I can. Limit as t approaches towards 1. Let's see, negative 32t squared, and then plus 4t, and then plus 268, which is basically what I came up with earlier, and then t minus 1. Well, I guess I'll leave it alone for the time being. I'll fix it eventually, maybe in the comments somewhere in the future, okay? Sorry about that. Don't want to waste your time. Okay. Let's go ahead and solve for the rest of this then. What is the man's initial velocity? So if I want to solve for the man's initial velocity, what that means is I need to figure out at time 0, what is his initial velocity then? So in that case, what I need to do is solve for the equation of the tangent slope. I'm sorry, I want to solve for what is the tangent slope at t is equal to 0. So using method number 1 right now, because again, I don't want to embarrass myself and mess it up again. Limit as h approaches towards 0 of h of 0 plus t let's see, h of 0 plus h, and then plus h of 0, all divided by h, okay? Let's see. So if I can solve for this limit, then I can figure out what is his initial velocity. So let's go ahead and make a substitution. Actually, let me just go ahead and write on the side right here just in case. H of t is equal to negative 32t squared, and then we have plus 4t and then plus 240. So let me just go ahead and make a double check just to make sure. Yes, that's our equation. So let's go ahead and solve for all of these guys then, okay? So h of 0 plus h, that is the same thing as h of h. So that is going to be negative 32h squared plus 4h plus 240. H of 0, that is just directly equal to 240 then. So limit as h approaches towards 0. H of h, I'm going to go ahead and plug it in. Negative 32h squared plus 4h plus 240 minus the 240 that we have for h of 0, all divided by h. So 240s cancel out. Everything has h in it. We can go ahead and divide through. So limit as h approaches towards 0. So negative 32h, sorry, let me make a mistake right there. So I'm going to go ahead and erase that. So negative 32h and then plus 4. As h approaches towards 0, we get 0 plus 4. So the answer is going to be 4. And that is going to be in terms of meters per second. Okay, and if you notice, that's actually not a coincidence that this 4 that we have an answer is actually the same thing as this 4 that's over here, that's multiplied by t. Because later on you'll learn that that right there, that number that's multiplied by t in the linear part of it, turns out that that's going to be our initial velocity every single time.